I'm sorry?
Chapter 33 isn't on the exam?
It's not going to be on the exam, yeah. And then so midterm 3 is going to be next Monday, right? And the stuff we're covering today is the last thing we're going to be, that's going to be on the midterm. So, okay. So midterm 3, Monday. What day is that? On the 8th or something? May 8th, right? And that's chapter 29, 30, 31, and 33, 33, 32, right? Okay. So make sure, I'll make sure to post all the lecture notes and all the worksheets for that for you guys this week, and that way you guys can use that to study, okay? Yeah. So yeah, actually I need to do a little discussion asking you which problem you want me to review, right? And then I'll post that by on the weekend. Okay, that way you guys can watch it before the midterm. Okay, so I'll post a discussion board for you guys to post which question you want to ask, and then I'll make it due on Thursday, so then I can just make the videos on Friday. Okay. All right. Cool. All right. So going back to electromagnetic radiation. Okay. So last time we wrapped up with this idea of the pointing vector, right? The pointing vector points in the direction that the wave actually travels, right? And we actually found out that we can calculate other things out of the pointing vector. For example, if we take the average of that pointing vector, we end up with this idea called the intensity of that light, right? Intensity is basically how much power, right? How much power something delivers over an area, okay? So if you have a very intense light, right, it'll give you a lot of power in a small area, but if you spread that intensity over a large area, then it's actually a lower intensity, okay? And then we did some inverse square law stuff. But now we're going to wrap up with, in this section, is this idea of radiation pressure, okay? And it's an interesting thing that light is not what you think it is, because when we think about light classically, in this class, right, they are actually massless objects. They don't have any mass associated with them. And what happens is that if you have no mass, right, in classical mechanics, right, the momentum of something is the mass times the velocity of something. This is going back from chapter 8 or 9 last semester, right? So if the mass is 0, right, that means the velocity, no matter what your velocity is, right, then the momentum of light is always going to be 0 somehow. But that turns out not to be true. In modern physics, if you decide to take that class next semester, right, you can actually prove that the momentum of light is actually just is energy divided by the speed of light. But we're not going to think about it that way in this class. We're going to think about it classically. Okay, we're thinking about, well, if you thinking about a force, right, that's actually the change of momentum over the change in time of something, right? That's one of the things we learn about momentum, is that when we apply a force, if we rearrange this equation, right, we apply a force over time, we get a change in momentum of something. Okay, so the longer I apply that force, the more I change the momentum of that object. Okay, well, change in momentum, we can just think about that as how much energy it absorbs over the speed of light in this case. Okay, we're going to do this kind of without proof because we can't do it without dealing with modern physics. But when we look at this number, now what I'm going to do is actually multiply these two numbers together, right? Multiply the numerator together, right? Right? Energy per time, right? That's actually power, right? So there's a lot of lowercase p stands for momentum, right? Uppercase P stands for power. Okay, so don't mix those two up because they look exactly the same, right? Okay, so that means the force that you can apply to something, if you were just a light, right, it's actually going to be the power that coming from that light source divided by the speed of light in this case. Okay, now, right, previously we already quantified what the power of electromagnetic radiation is. The power over the area is the intensity, which is what we just talked about. All right, we can calculate that with just calculating the average value of the Poynting function, right, the Poynting vector. So if we want to rearrange this in terms of force, what we need to do is actually plug in what P is up here. So P is actually the same thing as the force times the speed of light, right? If you did that, well, actually, we want to we want to keep the equation in terms of force, right? So force is going to be P over C, right? We solved this equation for P, so P is actually I times A, right? We'll plug that in there, right? So I, the intensity times the area you apply that force divided by C is actually what the force you're going to get from electromagnetic radiation. So a lot of times, right, this area, this A area here, right, we actually don't know what that is. So therefore, it's actually oftentimes better to just calculate force over the area, okay? I know we haven't talked about this in this class. When you apply a force over a large area, right, let's say, you know, pushing against each other, right, that's going to be a very low pressure situation. But if you take the same force and you apply it to a small area, that creates a high pressure because, right, that smaller, all of that force is being exerted on a tiny area versus a large area. And this is known as pressure, okay? Yet there's another P here, okay? This P here stands for the pressure of radiation, okay? With many P's, that's why we try to avoid P's whenever possible, actually, okay? So if we want to calculate what the radiation pressure is, this equation actually simplifies, where if you just calculate the intensity of the light divided by the speed of light, then you get the radiation pressure, okay? All right, and this comes up because you can actually propel objects with this radiation pressure, but just not very well, okay? I'm going to see how this works, okay? There's this idea of known as a solar sail, as opposed to a wind sail where you have wind hitting your sail and then transferring momentum onto the sailboat, okay? What you want to do if you're in space, since there's no wind in space, there is light coming from the sun, right? So let's say you have a star in the middle of your star system. Let's make this a black star, right? Right, you have light coming out of there, right? And so if you want to sail away from the sun, right, you can build these things called a solar sail, where it may look like a giant, you know, sail just in space. And as the sunlight hits the sail, it transfers momentum onto that solar sailing ship, right? And it will fly actually away from the sun. And you can actually calculate how big this sail has to be using this example here, which is what we're going to do here real quick, okay? So the idea is that, well, let's say if we built this this solar sail, right? And, you know, if we're around, you know, Earth's orbit, the intensity of light from the sun is about 1,300 kilowatts per meter square. That's just some, you know, number that depends on how far you are away from the sun, right? Further away from your sun, right, the lower, the less and less intense the light will be. But, you know, around Earth's orbit, you're going to get about that much solar radiation intensity. Let's say if we built our little spacecraft about 10,000 kilograms, so, you know, size of a maybe like a big those cargo trucks, right? It's not too heavy, okay? And if we want to sail towards Mars with some acceleration of 0.01 meters per second, okay? A very small acceleration. But this is going to be constant, right? And it's going to go faster and faster and faster as you go towards Mars, okay? And, oops. The question is, well, how big do we have to make the sail in this case, okay? So we start off, right, with the idea that, well, we're going to do a setup here where, let's say we have the sun shining its light, right, and here we are on Earth, right, and the sail, right, let's just make it into, just to simplify the geometry, let's just make it like a, yeah, we can make it a square sail, right? As the sunlight hits it, it transfers some of the momentum over, right? It actually applies a force away from the sun, okay? And hopefully at some point, you'll end up on Mars, right? Okay? So remember that force is going to be the mass times the acceleration of something, okay? So we're just going to try to figure out the magnitude of all this stuff, okay? Because we're only given the magnitude of the acceleration we want, okay? We also know the mass of the spacecraft, so we can actually calculate what the force is. So the force that we're looking for is actually 10,000 kilograms. That's an SI unit. Nice of them to give it to us in that. Times 0.010 meters per second squared, also an SI unit. Okay, so this will be about 100 Newton. Okay, okay, that's the force we're trying to calculate. Okay, so how big does the sail have to be in order for us to get that? Okay, so the solution to solve this problem, right, is that radiation pressure, this lowercase r, p, rad, right, is basically going to be the force on that sail divided by the total area of that sail. Okay? Okay. And we already know what the force has to be. Okay? And then the radiation pressure, go back up to the formula up here, right? Is the intensity of that light divided by the speed of light. Okay? So the left-hand side here is actually the intensity divided by the speed of light. Okay, and we're just trying to calculate what the area is. So solving this equation for the area, so we move back up here, because the force times the speed of light divided by the intensity, right? That gets us to there. Okay, if you plug these numbers into your calculator, you're going to come up with an area that's 2.3 times 10 to the 7 meters square. Okay, is that a big area or a small area? Yeah, because each square meter is about this big, right? So you have 23 million of these, right? It's probably going to be a little bit, maybe almost the size of a city, okay? Or, I mean, not city, like Turlock or something like that, okay? In fact, you can calculate, you know, maybe what the radius has to be, right? So if we're just doing, if we're pretending the sail is a square, right? Right, the area of a square is just the length of its square, right? So if you just take the square root of this, right, L is going to be square root of 2.3 times 10 to the 7. In fact, I need to calculate this. All right, square root. Where's my square root thing? Oh, there it is. Okay, 2.3 e to the 7. Okay, that's going to turn out to be about 4.8 times 10 to the 3. Okay, or 4.8 kilometers. Okay, that's approximately like 2.5 miles. Okay, so the length of the sail has to be 2.5 miles long, right? And so it's not super realistic to be able to have a spaceship that's only weighs 10,000 kilogram, right, and be that big. Okay, so unless, I mean, I think people are developing, like, you know, fancier and fancier and lighter material in order to do this, but so for now, we're not going to be solar sailing around our solar system too much. Okay. Any questions about this? All right. Okay. So one conceptual thing we want to think about, especially if those of you are interested in taking analog digital electronics next semester, is that these electromagnetic waves plus the alternating current that we've been talking about last chapter, the combination of these, right, basically allows you to make these things called antenna. Where would you find antenna around here? Who has an antenna on them? Like your phone has an antenna in it, right? Your all your Wi-Fi, basically all of today, anything that's wireless has some sort of antenna in it in order to communicate with each other, right? So how does an antenna, how does electromagnetic wave and the alternating current source comes together? So let's say we have some alternating current source here, right? I'm going to model this with some tiny resistance R, right, where I'm going to think about this connected to like just a bar of metal. Remember, metal is like another word for conductor, okay, right? As this alternating voltage source go up and down, what's going to happen is that you're going to create either positive charge here, right, and then negative charge on the other side, and then you're going to switch between the two, and you're going to be oscillating up and down, up and down, up and down like this, right? So if you think about, if you're tracking the motion of these positive charge going up and down, oops, I'm going to draw it on the side here instead, right? These positive charge going down, going back up, going down, going back up, right? These charges are creating, right, since it's a positive charge, it creates a electric field around them, right? Okay, and as this charge is moving up and down, it's also a changing changing electric field, right? And what does changing electric field create? Creates magnetic field, okay? All right, in fact, right, the magnetic field will be perpendicular to all these electric fields, okay? And this is actually what happens when you build an antenna. It creates a electromagnetic wave that goes outward from it as a way to basically generate electromagnetic wave by just having an alternating current source, you know, for example, a function generator or your wall outlets, right? It'll create electromagnetic waves just by connecting a piece of metal to it, okay? And that's basically how an antenna works, okay? So, you don't get to see this light because like usually the frequency is so low, it's not high enough for our eyes to see it. But then of course your devices is able to see them because they are tuned to pick up that particular frequency of light. Okay, so I'm just going to just showing you do this conceptually. So we're not going to do any math with it. But that's the idea. So in case if you do want to take the next class, which is the electronics class, you actually will be building this in order to transmit signal from like 6 inches, not that far, but but if you can build something that can transmit wirelessly, you know, 6 inches, then you can build it to transmit it for 6 miles if you want. You just have to boost the power up, right? Okay. Anyway, the last section we're going to cover in this chapter is polarization. Polarization is very important because, right, a lot of our technology actually also is based on how to polarize light. That way we can actually filter them using vertical versus horizontal polarization. Okay, so what polarization means is that, well, it is a what's that called? It's a convention actually, right? That what we think about as polarization is basically the orientation of the electric field. Okay, oops, I was trying to do yellow here, right? Right. The orientation of the electric field defines the polarization of a particular electromagnetic wave. Okay. So in this case here, right, the electric field is along the y direction. Therefore, we call that a vertically polarized light. Okay, because y is usually the vertical direction, right? But if let's say we can, you know, this doesn't have to be the case. If we rotate it, you know, we just rotated our light source so that, you know, the electric field is actually oriented along the z-axis, right, or flat in this plane, right? We call that horizontally polarized. Okay. So in reality, what actually happened is that the light actually itself rotates over time, and these are called circularly polarized light. And we're not going to try to deal with that because it's much harder to describe because it evolves over time. We're just think about light that's going to be either vertically polarized or horizontally polarized all the time, okay, or a combination of the two, okay. Okay, this is where we can play around with them because we can actually build these things called polarizing filter. Okay, what is a polarizing filter? Right, let's say you just have some light source, and if you just create a random light source, what happens is that it comes out unpolarized, meaning that the polarization angle or the vector, right, this E field depending on which light packets you're looking at, they all kind of point in just in a random direction. Okay, so if you just do, you know, you don't purposely create polarized light that will just come out unpolarized, right? Or the light just comes out in a random direction. Okay, what you can do is that you can pass this through a polarizer. Okay, and a polarizer is designed to basically absorb anything that is not along the line axis of its polarization. Okay, in this case, right, this polarizer has an axis of polarization horizontally, so it'll allow horizontally polarized light through, but blocks vertically polarized light. Okay, okay, right. And actually, the way that the book draws these polymers is actually on purpose, is because vertically aligned polymers actually creates horizontally polarized filters. Okay, so what happened is that at first you have some random polarization of light, but after you pass it through a filter, all of the light becomes horizontally polarized. Or actually, only the ones that are horizontally polarized can get through, right? So that's the idea. Okay. And this comes up with a way to calculate how this light actually passes through, and this is going to be called Malu's law. Okay. Okay. Because it's not just as simple as, oh, if you're horizontal, then you go through. If you're vertical, you don't go through, right? But what about the ones in between, right? What if, right? What about this one, this light here, right? That's not quite vertical, not quite horizontal, right? What happens to that one, right? What happened to this part of the light? Okay, this is where we have Malu's law, where let's say we have a incident light, right? Right, that goes through a vertically polarized, right? So this is the polarization axis going straight up like this, right? Let's say our light comes through not exactly at 0 degrees and not exactly at 90 degrees, right? At some angle between the two, okay? What happened is that the filter will actually pick out the part of the, sorry, it will pick out part of the light that is going to be, part of it is going to be perpendicular to the polarizer, part of it is going to be parallel to the polarizer. Therefore, the part that is perpendicular gets filtered out. The part that is aligned parallel to the polarizer gets preserved. Okay, so what happened is that when you have light coming in, the transmitted will be only the part that is parallel to that polarizer, and therefore you only get whatever the initial amount of electric field is multiplied by cosine of theta. Okay, right. But one thing to remember is that the intensity of the light is proportional to the electric field square, right? That's one of the things we learned last time, right? Therefore, if we want to figure out the intensity of the light that goes through, right, we cannot just take cosine theta. We actually have to square both sides in order to get the intensity, whatever the intensity of the incoming light is, times cosine square theta. So that's where that square comes from. Okay, the relationship between intensity and electric field. Okay. Okay. So let's say we have some. I'm going to do a little example here. Right. Let's say I have some unpolarized light coming through. Right. I put it through a vertically polarized. Right. This is the axis of polarization. Right. Can I figure out how much light what is the intensity of the light that gets through? So this is going to be I naught, right? What about I transmitted? Okay. Okay. Is there a way for us to figure that out? Okay. So remember that the average of a cosine square function, right? If we just have unpolarized light, right? We're just picking random angles, right? Okay. Remember the average of a cosine square function is 1/2 whatever the amplitude is, right? Right. So since we have cosine square here, whatever gets transmitted is going to be knocked down by 1/2 factor of whatever the initial, right, intensity is. Okay, so if you just take any pair of polarized sunglasses, take it outside, right, and then you just measure the light intensity before it hits the lens and after the lens, you basically always lose half the intensity of the light. Okay, all right. So what you can do is actually, you can play this trick where you have multiple polarizers, okay, where let's say the first polarizer basically is a way to basically only make it so that the polarizer create a light source that is polarized at this angle theta, let's say, okay? Then you put it through a second one, okay? And now the incoming wave is actually, right, going to be polarized, and then you actually have to calculate the polarization angle between them. So an example of this is that if you have, I think these are both vertically polarizers, so this line is supposed to be the polarization angle, right? If you stack both of them up together, right, it's actually not going to affect it. So hopefully you can see a little bit here where, this is sort of the intensity if you didn't have a polarizer on it. This is about half intensity, okay? Putting another polarizer that is oriented the same way does not change the intensity, right? But if you put the other one 90 degrees to it, where now, right, whatever light's coming out here, they're all vertically polarized. If you put a second polarizer on there that's only picking out the horizontally polarized, you actually completely block the light, okay? And then the case somewhere between the two is going to be partially blocking the light itself, okay? All right, so what I'm going to do is do an example before, and that way it shows you how that works. So a neat situation is that those of you who ever wore like polarizing sunglasses and look at water, somehow you're able actually to see through water somehow, right? So why is that? And we're going to learn more about this in the optics chapter, right? But, okay, the reason that you cannot see through water is not because water is not transparent, it's because of what? Refraction, or also known as glare, right? The glare off the water. Okay, so I'm going to try to draw a little a picture here where let's say you are at a dock somewhere, and then there's you're looking at some water, and then the sun, the orange sun, is over here. Okay, what happened is that as the sunlight hits the water, okay, so it hits a horizontal surface, right? So electromagnetic radiation that are vertically polarized are more likely to be absorbed by this horizontal surface. So this is going to be, so sorry, I said horizontal, didn't I? Vertically polarized light is more likely to be absorbed by this surface. But horizontally, right, let's do another light rays here. The ones that are horizontally polarized, this is where my ability to draw things is going to hamper this situation. It's less likely to be absorbed, and it's actually more likely to be reflected, okay, or it's known as glare, okay? So when you are on the little side of a body of water, right, the glare is actually mostly horizontally polarized. Oops, I'm trying to draw that, okay? So what does the polarized sunglasses do is basically filtering out these horizontally polarized light, okay? And therefore you can actually, it makes the surface of the water more transparent because you basically remove this glare, okay? All right, so let's try this with a little example here. Another example that's a little bit more towards solar energy, okay? So if you want to calculate how much power your solar cells, right, your solar panels are getting, in a particular location, you can actually calculate that pretty easily, okay? If you go to this website called Engaging Data Solar Intensity, it actually can tell you the exact intensity of the solar radiation at a particular location. So I picked Turlock, right? This is 37.25 latitude, and then negative about 120-ish in longitude, okay? And so we're getting about 768 watts per meter square here. So if you take a solar panel outside, right, you're going to get about 768 watts per square meters of solar panels you're using. Okay, so if you want twice that, you can put 2 square meters of solar panels. Okay. Okay. So what if we just play around with it and put some polarizers on top of it? Okay. So let's say, right, we have once again sunlight, right, which is unpolarized, right? We have this bright yellow sun, right? It's just sending rays towards us, right? If I put a polarizer that is oriented 30 degrees relative to north, right? Let's say this direction is north. This is the polarization angle, right? What would be the intensity of the light that comes out on the other side? Okay. Anyone wants to venture a guess? What factor will it be? Do I have to punch this stuff into my calculator? Why not? It's 1/2, right? When you have unpolarized into polarized, it's always 1/2, okay? So therefore, the intensity transmitted is just 768 watts per square meter divided by 2, okay? And this is where, okay, I'm going to make sure that I didn't screw up the calculation, okay? It's 350 plus 34, right? Is that right? Okay. Okay, so that's the amount that will be transmitted if you just put a single polarizer on it, right? Now all of this light, okay, that's coming through, right, instead of being unpolarized, right, it's actually polarized at a 30 degrees angle now. Okay, okay, so there's some angle here of 30 degrees, okay? It's really hard to draw in 3 dimensions. But what I do is I'm going to put in a second polarizer, right? Instead of orienting that polarizer at 30 degrees to north, I'm going to orient that polarizer 45 degrees to north, okay? So I'm going to take this light here, right? Instead of it being transmitted, right, I'm going to call this, the incoming wave, the incident wave, part 2 or something like that, right? Okay? And now, right, now it's a light source, right, that is polarized at this weird angle, 30 degrees. I'm going to put it through another polarizer, right, and it's supposed to 30 degrees, right? This is going to be theta 2 or something like that. This is at 45 degrees. So how do you think I should calculate the transmitted light through the other side? What will be I trans, comma 2? How would I calculate that? What angle should I pick, right? Because basically it's going to be I naught 2 times cosine of some angle, right? Square. Right? What angle should I put in? Should I put in 30 or 45? Why 15? That wasn't the problem. Right, because this light is actually coming in polarized at 30 degrees. So as it comes in, it's actually the difference between those angles you care about, right? 30 degrees to 45, right? That's a 15 degrees difference in polarization. Okay, so if you did that, okay, 384 times whatever cosine of 15 degrees is squared. Okay. Ooh, don't give me the exact value. That's not useful. Okay. Oh, sorry, I'm in radian mode. That's bad. I'm going to change the degrees real quick. Okay. All right, you get actually 15 degrees. Sorry. Okay. You get 358 watts per square meter. Okay. So notice that it didn't drop off that much, right? Because only at 15 degrees square, right? That's not going to give you a loss as much as like 45 degrees or 90 degrees or something like that. Okay. All right, any questions about this? So it looks like I'm not going to start chapter 33 today, so we should jump in.